Welcome to the end of, I'm not even sure what week we're in anymore, right? It's, I don't know, more than the second, but not quite the 10th yet, somewhere in there. Um, so we're going to look at implicit differentiation today, 11.6. This is the last of chapter 11, which is primarily techniques for taking a derivative. It's a skills-based thing we're going to do. It's not overly new, but there'll be some new notation. But we'll go through that. What the skill we're learning today, we will use again when we get to 12.5 related rates. That's where you really need it. And so what you see in the interim, we have some applications dealing with the maximum and minimum, which basically you just look for where the derivative is zero. That gives you a maximum or a minimum, and we've got some tests to figure out which one is those. We're going to do a higher order derivative, which just means we're going to take a derivative of a derivative. So in a sense, it's nothing new, but we're getting something new. So if I take the derivative of my position function, I get velocity, which is my speed. If I take the derivative of that, I get my acceleration, which is how my speed is changing, whether I'm speeding up or slowing down. Okay, so that's 12. And then we do 15. I'm sorry, 12.5. And let me turn this thing off. And then we're ready for the next exam. There's also 12.6, which is elasticity. We'll address it a little bit. There's a video on it. It's extra credit. It won't be on the test. I don't remember if I did it now or if I'll do it later, but I will extend the due date on that all the way to the end of the course. So if you want to wait and deal with it later, you could do that, but it's extra credit. So we'll go from there. All right, so any questions about where we're at, where we're going, where we've been? All right, so we're here now. We're ready to start. Before we get into the content, you might notice I'm wearing an orange shirt today, and it's not just because I like bright colors. I also went to Oregon State, which was colors were orange and black, but it's also today's Orange Shirt Day. They do it for many different causes. For this one, it's for Native American boarding schools, recognition of it. Both my grandparents, in fact, my mother was conceived at boarding school, so both my grandparents were shipped off to boarding school when they were about 12, 10, I think grandpa at 10, grandma at 12. They were taken on cattle trucks from their homes, shipped over, in some cases, 3 state lines, and put in military-style schools. There was abuse. At least they did survive. Grandma's 102 years old and still alive. Grandpa made it to 86. So those are long life expectancies for their generation. But part of the reason I'm a teacher is because of the desire to change systems of education. So one of the things you'll notice that I implement in my class, I don't have an attendance policy that you have to be here. You have to learn, but you don't have to be here. Attendance came from these things as they were trying to keep the kids, and again, not just Native American boarding schools, but schooling in general is oftentimes just let's keep them in. It was almost like a mini prison because we don't want you out running around doing bad things on the street, right? So to me, attendance policies do that. You have to be here, and if you're not here, I'm going to take some points off, and so you come because you're going to lose points or something like that. You need to be coming to school because you want to learn. You can learn here, but you can also learn outside, so you need that flexibility. So anyway, if you see some things that I do or don't do, I'm always open to learning ways I can be more inclusive in building an education system that works for everybody and respects the humanity of each of us and our ability to choose and be self-directed. All right. So if you're wearing orange, great. If you didn't know about it, that's fine. I most probably haven't heard of it, but usually it's about this time in what month is this? September, towards the end of September. So if you see people in orange shirts, maybe ask them about it, if they might have had someone who went to boarding school. But it's also a great way. I mean, that's my grandparents actually were from the same reservation, but they lived on the opposite sides. They never probably would have met each other at home. Because actually my grandfather's Cree, so his family spoke a different language. Grandma could understand it because she was around him long enough, but they met at boarding school, and that's where they connected. And like I said, my mom was conceived there. We know that Grandma, she was born only 8 months after they were married, so it was either a very quick pregnancy or it was a shotgun wedding, we say. So, but there was some good things that came out of it. We've got relations, and we deal with it. Okay. So now I want to show you, first of all, as we get into what's called implicit differentiation, before I talk too much about why we use it, I want to show you that, in a sense, it's nothing new. Okay, so I'm going to do just a little example here. And let's just pick a fairly simple function or equation. Y equals, let's go with 3x squared minus 2x plus 4. And we're going to take the derivative. And so taking the derivative of both sides, the derivative of y, we could, when we're doing it, we call it dy dx. We've seen this notation before, have we? Yes? Okay. And then if you want to think of it, we also take the derivative of y, but the derivative of a variable to the first power is what? 1. The 1 comes down, it's y to the 0 power, which is 1. So it's really, I'm going to put that here. We did take the derivative of y, and we put this marker, the derivative of y with respect to x. dy, that's what dy dx means. It's an indication that we actually took the derivative of y. We never talked about this before because we just said, oh, that's what we're doing. But today we're going to need to, because in today's lesson we're going to have more than one y. We might have a couple, so we got some y's and some x's going on. And then what we do on the other side is we take the derivative of x with respect to x, and we could think of that as dx over dx, but what would that be? Fraction with the same thing in the top, the same thing in the bottom is always going to be 1. So we just come through and then we take 2 times 3 is 6, x to the first power. This derivative, the 1 comes down, we get a negative 2, x to the 0 power, and then we take the derivative of 4, which is 0, and we're done. We just did implicit differentiation. That's what we did. We've already done this, haven't we? We just didn't call it, and we're going to see today the calculus step of taking the derivative of getting an answer like this is what we've all been doing. The thing is since there's going to be multiple y's, the new part, or the difficult part, is we're going to have to do a lot of algebra to reformat things so that we get only one dy dx on one side and everything else on the other. So it's not the calculus that we're going to learn today that's anything different much. It's going to be the algebra after the calculus. We're going to have to move things around. And we're going to have to do everybody's favorite, factoring. Right? Who likes factoring? I don't even like factoring. So it's kind of like a puzzle if you do it, so it's not that bad, but I don't know. It's never been a great joy in my life. So I would rather do something else. I'd rather mop my floors than do factoring. No, we'll get there. Okay. So now it's a little motivation, if like an actor's motivation. Why are we doing this? We sometimes get equations or expressions that have, in this case, multiple y's in it. So we got y to the 5th plus y plus x. This could be some kind of a business function or any kind of function. And the thing we can't do with that, we can't get it as just y equals something. Okay? It wouldn't simplify. We can't algebraically simplify it. So when we run into something like that, this is where we need implicit differentiation. Okay. We're getting better and better graphing tools where we could actually graph things like this. You can enter this into Desmos, and it will actually graph it now. Your TI-84s, they won't graph it. You have to get y equals of some form. So, but other tools would allow us to graph this, and the textbook has given us a picture of what it would look like, and we see, oh yeah, it's a function, it's going sideways. So that's what it would look like. And so how do we take its derivative? I don't have a lot of room here, but I'm going to do my best to give it a try. So we'll start with this, and then we might have one or two examples. And what we're going to do today is we're actually going to go into the homework. We're going to work it together, a few of the problems, a few of each type. So you'll actually see it. You'll get some of your homework done, take some notes, but my goal would be is that you go back and put your notes away and try to do it on your own from your memory. If you need to look at your notes, you can look at your notes. But there'll still be enough other practice in there for you to do it. And again, when we get to 12.5, we're going to do it again. So you'll have plenty of time to do this. But part of the thing I do when I teach is something based on actually something from the ancient Greece. They called it underwriting. So the master would write, and we did this as kids, right? Remember learning your alphabet? You had those books that had the little things right under, so you saw the letters, and right underneath, that's called underwriting. So that's a nice way of learning where you just sort of mimic for a while. You see the process, you repeat it, and that's part of our learning. So let's see if we can kind of do this and see that it's not really anything too new. I'm going to rewrite it up here. And we'll walk through sort of the method that we're going to do. So we're going to take the derivative of each term, right? A term is something added or subtracted. Every term is going to be, we're going to take its derivative. So what would be the derivative of y to the fifth? Good. Just like we've been doing, the exponent comes down, we subtract 1 from it, so it's going to be 5y to the fourth. But we took a derivative of y, which we haven't been doing, and we've got an x in here. So we also say, hey, people, we took the derivative of y with respect to x. You're going to see this is the important part. We need to sort of put something there that says we took the derivative of y. When we take the derivative of x, it'll be sort of assumed, but again, we'll get a marker for that. Then we're going to take the derivative of y, just y to the first power. What do we get when we take the derivative of y to the first power? The 1 comes down, we subtract 1 from the exponent, we get y to the 0, which is 1. So its derivative is 1. And again, we put this marker, and this is especially why we need the marker, because there's just a 1 there. What is that? That is us taking the derivative of y. So we put this marker. Okay, and we're going to see the importance of that in just a moment. Okay, we get over to x. We take its derivative. What's the derivative of x to the first power? It's 1. And again, I'll do this. We won't do it all the time, as you'll see, but I'll put a marker here too that this is the derivative of x with respect to x. And does it make sense that dx over dx would be 1? Good. And that's why we're not going to do it all the time. But I just want you to I just want to sort of give evidence when I take a derivative. And you may want to do this because we're going in some of these ones we're going to have a product rule. And you might not, oh, did I take its derivative or did I not? And, you know, you could always put a dx and then let it become 1 and disappear later on. We're not quite done yet, though. We've got to take the derivative of 0. What's the derivative of 0? That's a hard one, isn't it? What's the derivative of a constant? If I have any number and I take its derivative, we always get 0, right? Because a constant is a horizontal line, so it would have a slope of 0. The same thing with 0. So I guess I was so impressed with e to the x, and I just realized 0 is also its own derivative. So maybe e to the x isn't so special. Here's the other function. the zero something equal y equals 0, that's a function. It's its own derivative too. But you'll see we'll have these equations, and sometimes there'll be a number there. You got to take its derivative, you get 0. Sometimes it'll be another function. So, but the thing is what we're looking to get is we want to get dy dx isolated and by itself. So our final answer will be something like dy dx equals stuff. Everything else is supposed to be over there. So now we have just finished the calculus part. We've taken the derivative. Everything from here is all algebra reorganization. Okay, so dy dx, we want to get that by itself. We'll go ahead and say dx over dx is 1, so this is 1 times 1. It's something without a dy dx, right? So what could we do to get it away from this side? Subtract it. Just subtract 1 from both sides. Okay, so I'll kind of go over here now. So we have 5y to the 4th dy dx plus 1 dy dx. Again, we don't equals -1, right? Because 0 minus 1 is -1. But we still have 2 dy dx's. What are we going to do so that we only have 1 dy dx? Everybody's favorite, factoring, right? So factoring works if we would have had, say, 3x plus 2x. We could factor out the x, and we get 3 plus 2, factor the x to the back, which is 5x, or however you want to do it. Okay, so that's what we're doing, is we've got a common factor, dy dx. We're going to factor it out, and what that looks like is we'll do it to the back side. So here's dy dx. That got factored out. What's left in here, well, the dy dx goes to the back, so we've got 5y to the 4th, and then we've got plus, this is what you might forget, there was a 1 here, there's always a 1, so when this gets factored out, so these are getting factored out, there's a 1 left behind. So did you see that, how that common factor dy dx factors into one factor of it? If you don't quite see it, distribute it back and you'll see you'll get back to where you started. It's just a different it's a equivalent representation of that, but it's one of the harder things to pick up on. I remember when I was learning this the first time as a student back in the 80s, I still remember the day where it clicked, and I go, oh, this is such a cool tool. This is why we do factoring. But it took a while. It didn't just hit. But once it did, it was like, why couldn't I do this? But now all the things I didn't understand, there was a lot of things I was able to do now that I kind of got to this. This is where the factoring sort of clicked. And then we're not quite done yet, though. What do we need to do? We just need to divide by all of this, right, on both sides. This cancels with this, and we're left with dy dx, and I'll put the answer down here, because this is what we were looking for, minus 1 over 5y to the 4th plus 1. So what you're going to see as we do these ones, typically, because if there's multiple y's, we've got multiple dy dx's, we bring them together with factoring, and we're going to divide. In most cases, our answers are going to be fractions. Not necessarily all cases. I mean, there could be an exception, But most of the time, you're going to see we end up with this sort of fraction where we move everything else over, and then we have this last step of dividing, so we're left with a fraction. Okay? But this, as far as taking the derivative itself, did that feel like there was anything completely new? No. Just sort of this new thing that whenever we take the derivative of y, we put this marker. What this is helping us, this is multivariable calculus, 2 variables. We could get to 3, 4, 5, and in business processes, if you're running a factory, you could have 100 different variables out there. You'll use a computer to do all that stuff, but it's getting you there that if we can do it with 2, we can do it with 3, 4, 5, we can do it with more variables, and that's a more realistic situation, right? It's what you're going to be working with. If everything was just 1 or 2 variables, our world would be a very simple place, but most things in the real world are many multiple variables. But it's really hard to think in multiple variables mathematically. Okay? So that's what we're doing. And again, I've already sort of introduced this. I use this method of using dx. When I'm taking the derivative of x, it's just I call it a marker just to say, yes, I took a step and I took its derivative of x. And then I use dy dx, and notice a slightly different color there. That's going to mark whenever I take the derivative of y. And we're going to see this becomes important because now we're going to throw in some things that'll get us practicing the product rule in a little different way, because we'll have x times y. We've got a few examples we'll look at. But that's really all we're doing. And then again, so we take the derivative just like we've been doing. We put these markers, whether we're taking the derivative of y or taking the derivative of x. Then we do everything else as algebra so that we get dy dx equals the derivative. Oops, we're done, sort of. We go into WebAssign now. We'll pull our examples directly from there. I guess we can keep those for now. WebAssign. Oh, you're probably, sorry about this, but you're probably wondering about the exam results. I just forgot about it. I figured we'd figure it. No, I did forget about it. The coordinators there was question number 10, there was some pushback, let's put it that way. They took a look at how people did, and some of you did well, some of you maybe just didn't quite. It was a product rule question, but it was asked in a new sort of form, and you might not have recognized it as a product rule. So it was worth 8 points. They narrowed it down to being basically worth 8 points. So every exam will be out of 95 points. So if you've scored 100, you'll get actually over 100%. If you scored 95, you've got 100%. So that was their way. The results came back that it was about that particular question was running about 4 points on average because you either got it or you didn't, and so it was kind of an extreme thing. That's how they decided. I'm still working on it. Well, last weekend I was gone, but I will get it done this weekend. My goal is when I get home tonight, Friday, to spend it, and my goal is to try to get it done Friday night so I have some time over the weekend to do something other than work on math. I don't love math, no. Math is okay, it pays the bills. Teaching is what I love. But I'll get those to you. And what I've got a little foot scanner that it has a little foot control where I can take a picture. So in the grade book, not only will you get your score, you will also get a scanned image of your test. So you can start reviewing it in advance. It makes it easier than me passing them back because, as you see, if I pass them back today, probably about half of you wouldn't get it, and then I carry those for the rest of the semester. So this way everybody will get their test back as well. So you'll get it over the weekend. My goal is for maybe by Friday night, but I don't always make my goals, right? So that's why I do the extension. I understand. But I got working on the Monday class because I had those earlier, and it's pretty standard of what we've done. Is again, some people really understood. Some I could tell You got stuck on a question, but you probably understood it, but you didn't see it the right way. So we'll work forward. And again, remember, I do this holistic grading. So as we go forward, as you pick up anything that you didn't completely understand before and get better at it, it will get incorporated into your scores and your grades. So what's my email? There it is. Gets me in. And the reason I kind of do this is it gives us a good start. We're on, what are we, 11.6. So we'll, and it gives you some agency here too to decide which ones we should work on. So my first question is, do you want a simple one or do you want to start with a more complex one? Simple. Okay, that's the way I'd go. Because if it still seems simple, then you haven't wasted any time. So let's go ahead and start with number 1. This one here. And I'll write it a little bit larger up here. And this one you'll see is fairly simple because there's only going to be one dy dx. We don't even have to factor. And there is no product rule that we have to use here, right? So what's the derivative of 4x squared? 2 times 4 is 8. X to the first power. And we could put dx, but again, we're going to just turn that to 1 anyway. So we just said, okay, I took the derivative of x. That's sort of my free one. I don't have to make a marker. Next, I take the derivative of y squared, negative 2y. But this time I need to say, I've got to put this, that this was actually the derivative of y with respect to x, because that doesn't just become 1, that becomes, it tells us what we're getting. We're getting this slope, right? This is the slope of the tangent line, dy dx, a change in y over the change of x. That's really what we're looking for. And then on the other side, we take the derivative of 5 and we get 0. See how we, as we get to this brings in a lot of the things we've learned, helps to solidify them and maybe build understanding where there wasn't. We want to get dy dx by it. So this is, we finished the calculus part of this problem, right? We've done the derivative. That's the calculus. The rest is algebra. So we want to isolate dy dx. So again, let's get rid of this 8x. Let's get it to the other side. Get it out of that side. That becomes 0. So we have negative 2y dy dx equals negative 8x. And then the last step, divide by negative 2y. And again, you start to see we get these fractions. This is 1. We're left with dy dx equals this, and we can simplify it. Negative divided by negative is positive. 8 divided by 2 is 4. X over y. So that's what we would put in as our answer here. Done. So that one, not too bad, right? So let's, as Emerald says, let's kick it up a notch. You watch his shows? I don't know if he's still pop. My dad used to love them. Louisiana Cooking, and we lived in New Orleans when I was a kid for a little bit. So as we say, let's kick it up a notch. So we're going to take a look at 2. And with 2, it's really the same process, but as you can see, we've got a y and another term with a y, so we're going to get 2 dy dx's. So we're going to need to do our factoring trick. But on top of that, we've got an x squared times a y. We have a product rule that we're going to have to address. So I'm going to write it a little bit larger up here. Now, I'm going to emphasize that this is x squared times y, so this is a product rule. And in the product rule, remember, we take the derivative of the first function, leaving the second one as it is, plus the first function as it is times the derivative of the second. So we're going to get 2 terms. So whenever you see a product rule, a function times a function, we're going to get 2 pieces, 2 terms. So I'm going to do this without breaking it down and setting it up separately. I mean, you could still do that. I can work with you. And just to let you know, I've got on Friday, tomorrow, someone's already contacted me. I can't remember which class. But 2 o'clock I'll be on Zoom. In fact, actually, I'll start up a little bit early. So if you has questions, about 2 o'clock I'll be on Zoom. So 2 or 3, just let me know. Again, I'm also going to be grading papers, but if you need me, let me know. Friday afternoon we can meet up and walk through some of these. So I'm going to take the derivative of the first part, which is x squared. Its derivative is 2x. The y just tags along for the ride. I didn't take its derivative, right? So this is the product rule. Derivative of just the first part times the second part unchanged. Then it gives me a plus, and I'll get the second part where I put the first term, x squared. It doesn't change. I just write it down. I just copy it, and I'm going to multiply it by the derivative of the second term. The second function. What's the derivative of y? It's 1. I'm going to actually write that 1, and since I took the derivative of y, that's where I need to put this marker. I need to announce to the world I took the derivative of y with respect to x. Actually, I need to announce it to myself. Okay, so far so good. That was the new part that sort of complicates this product rule. 2 things are being multiplied, so I got to separate them like that. We'll do this a few more times. I believe what this did for me, implicit differentiation, was where a lot of things came together. The product rule comes together. You're going to see the chain rule will come together here as well, and some of the algebra skills of factoring will hopefully come through. So that's just the derivative of the first term. Now we need to take the derivative of the second term, right? Y squared. This one's a little nicer because there's no product rule. It's just y squared. So the 2 comes down. Y to the first power. Since we took the derivative of y, we let the world know by putting dy dx. Okay. And then the last step is to take the derivative of what's on the right side. Derivative of 8 is 0. Okay. So we've took the derivative of every term, both on the left and the right side. Calculus is done. The rest of this is algebra, moving things around. Do you know what algebra means? The word, if you go into its root, it means to break into pieces and to put back together. In the Old West in the U.S., in America, there was an algebraist. If you had to go to the algebraist, you know what happened to you? You broke a bone. An algebraist would break it again and then reset it. Anyone had a broken bone? Unfortunately, never. That's what they do, don't they? They have to break it apart and put it. So they called them algebraists, the people who, they didn't have anesthesia. So I'm glad I'm not living in the old West and fell off my horse in the, and have to go see an algebraist and have him break my leg again and then put it back together. But that's algebra, right? We're breaking things apart, putting them back together. Sorry to bring up painful memories, but it might help. This algebra is sometimes painful, right? Okay. So now we're working on the algebra part. Anything, and again, I always go back with a different color pen or a highlighter. I highlight the dy dx because that's what I want to focus on. I want to get these two different dy dx's to become one dy dx, and I can do that through factoring. And I want anything that doesn't have a dy dx to get out of there because it's just in the way. So I move it to the other side, and then I will divide off whatever's in front of the dy dx. So as you do these, it's the nice thing is each one sort of has a similar rhythm. You take derivatives, so there's a calculus step, and then there's this algebra step where we're kind of just doing a sort of a dance of moving things where they need to be. So 2xy goes to the other side. Notice it's positive here. It'll become negative over here. Okay. That's 0, and I'll just come down here. I'm going to do x squared. I'm going to get rid of that 1 because it kind of is in the way. So just x squared dy dx, okay, minus 2y dy dx is now equal to negative 2xy because that's 0 minus that. So it's getting a little bit cleaner. Some of you may want to go ahead and do the factoring in the same step, and when you get there and you're able to do it, great. I find if I do it now, I lose half of you because you don't, so I want to do it sort of step by step, even if it requires us to write things down a little bit. And again, even on this step, I want to go back and highlight, hey, this is what I'm trying to do, because sometimes I forget. With algebra, we get going and then we forget what we're trying to get done, because we get distracted by some of these other things. We're trying to get dy dx by itself. Oh, that's right. Okay, we can now factor them to the back side, right? We're going to factor these out, and so what's going to be left is x squared minus 2y. The dy dx is factored to the back side or the front side if you want. It's okay to go either route. So far, so good. One last step. Whatever's in front of the dy dx, divide it so it goes underneath on the other side, and we finished our algebra. Right? We're going to divide by x squared minus 2y. We're going to divide by x squared minus 2y. This side becomes 1, and so our final answer that's our answer. And again, that's what we would type in. Not there, up here. And what you'll see is this question is, you're going to have exactly the same answer, because the only thing that will be different is the number 8 will be some other number. So when you take its derivative, it's still 0. You'll get the same answer, but this is where I mean is you now have a template how to go through and do the product rule if you get stuck on something that you can now come back and refer to. And if you didn't take notes on it, it's fine. It's recorded. You can go back and watch the video and see how it was done back and forth till you get it. But try to build understanding. It's will get you through. So far, doing okay? Okay, so the calculus steps are really nothing new. It's just sort of this thing. It's the algebra of getting everything together. Okay, let me, well, I guess I can These other ones are just going to be a little more challenging. Here's a product rule thing here. That's not too much different. This one just has P's and Q's instead of X's and Y's. So you're going to do dP, dQ. So P's playing the role of the X and Q is playing the role of the Y's. If you want, you could just change that. But in business, you oftentimes use P for price and Q for quantity. So you'll see these popping up. But it's just they've used different variables. Oh, shoot. Here's one with a E to a power. That's kind of different, isn't it? You want to see one of these? No? Okay, we'll just keep going. Of course you do. Okay, we've got 6 and we've got 7. Any calls? Which one would you rather see? Which one? Have me do the difficult one so you can do the easier one. I figured you'd ask. Okay. Whoops. I'm going to need to hydrate a little bit for that one. Okay, so we're going to do 7. Let's move it on up. And you'll see it's got all the things. Now, the thing that probably caused you to try to ask for 7 was this y squared in the denominator. It looks like we need to do the quotient rule, right? Is that what you're thinking? Maybe. But we don't have to do the quotient rule because it's just y squared. What can we do to that y squared in the denominator so we don't have to do the quotient rule? Move it, yeah, use what I call the elevator rule. So the first step is to do a little algebra. We're going to rewrite this as y to the negative 2 e to the x. Okay, and that's going to be equal to 8 plus e to the y. A little bit friendlier, but still we have a product rule here, right? Y to the negative 2 e to the x. That's two different functions, two different variables. We're going to have to use a product rule there. And we've got something with an e to the x, which again is a simple derivative, but it also complicates things because you can't tell the difference, right? So let me come here. I'm going to, since it's a product rule, right? Y to the negative 2 times e to the x. These are two functions. I'm going to get two terms. So the first term, I'll take y to the negative 2. The negative 2 comes down. I subtract 1, so negative 2 minus 1 is negative 3. So be careful there. Sometimes you might be tempted to put negative 1, but they're both negative, so we're getting more negative. This is y to the negative 3. E to the x, we don't, again, the product rule says that's the second function, so it's the derivative of the first times the second one unchanged. But, oops, I almost forgot. Actually, I didn't. I like to write these back here. The first one is the derivative of y, right? So we put our marker, dy dx. Now, if you wanted to, you could have put it before the e to the x, but I like to have all my function stuff and the dy dx on the back side. So that's the first term. We're still on, we're taking that derivative of the first term, so we've got that part. Now the second part of the product rule says it's going to be plus this one. We take the first term unchanged, so that's y to the negative 2. Nothing done to it. I just copy it, bring it down, right? But now I take the derivative of e to the x. What's the derivative of e to the x? E to the x. See, it's simple, but it's also complicated because when you look there, you don't remember, did I really take that derivative or not? I didn't change. You just have to get comfortable with there's an e to the x in the first one and there's an e to the x in the second one. One's a derivative, one's a is not the derivative, but because they're the same thing. Any of you got a twin brother or sister, identical twin? Usually I'll get someone and they talk about how they can, mess with their teachers because if they didn't want to, they could send their sibling in for them, and if you're really identical, sometimes people can't tell the difference, right? Confusion. That's e to the x. Its derivative is the same thing. it can cause that confusion. But if we just focus and go along, we can do just fine. So, and we don't need a dy dx. If you wanted, you could put dx dx, because we took the derivative of x on this second part, right? Not the derivative of y. So we're done with the calculus on the left side. On the right side, we now need to take the derivative of 8, which is 0. Again, you don't necessarily need to write that because we're also going to get a plus. We'll get this next term, but I'm going to put it just to show that I did take the derivative of 8. What's the derivative of e to the y? E to the y. But whenever I take the derivative with something with y in it, I have to put what I call the marker. I have to say, hey, I took the derivative of y with respect to x. That y only lives as long as there's an x somewhere, I guess. Okay? But again, see, you can see how it's simple but a little confusing. Because you look at that, did I really take the derivative of that? Yes, we did. But e to the y, its derivative is e to the y. Okay? But even though you may up here kind of acknowledge it, there's probably some part of your brain that says, you're just making this, you know. How many of you got these voices in your head? And this doesn't mean we're crazy. We all got voices. We got these ones that are second guessing us, and at least I think we all got voices. Maybe I am crazy. I don't know. Anyway, we'll go. So those are those voices that talk to us, and we have to be cognizant of them because we have to answer them sometimes. We have to give them a good explanation. That is it. So again, now we are done with the calculus part. And I'm going to come back and I'm going to highlight everywhere there's a dy dx, because those are the things I'm trying to do the algebra to get these. It's all about getting dy dx on one side of the equation by itself. Could be the left side, could be the right side, but I want to get it onto one side by itself, so then everything else is over on the other side. That's the whole goal after this part. What I see here is I've got a negative here, so if I add it to the other side, I won't have a negative. I personally don't like negatives because those cause me a lot of problems. I forget to write them down or something because they're small. So if I can get rid of a negative, I will. So, and there's a dy dx on this side. This side's positive. So what I would do, again, it's not the only thing. You could bring the other one the other way. I'm going to add 2y to the negative third e to the x dy dx. This whole thing, I'm going to add it to both sides. I'll just write it over here because this now becomes 0. And what we're left with is y to the negative 2 e to the x. And that's going to be equal to, let me do it this way, e to the y dy dx plus 2y to the negative 3 e to the x dy dx. Okay, so that really was just an algebra move, moving that one term over to the other side. I also didn't rewrite the 0 because it's not really needed. When you add 0, it doesn't change anything, so that's why that disappeared. Okay, and again, I want to come back, re-emphasize what I'm doing. If you got a highlighter pen, that's a good place for this. Highlight these guys. We want to get these two. We're going to want to factor them out now so that there's one of them. And then we got this other term that we can then just divide. So you kind of see this sort of rhythm of processes. So we are, at this point, we're going to factor these guys to the back. So we're just going to rewrite y to the negative 2, e to the x. What's left here is e to the y plus 2 y to the negative 3, e to the x, all in a parentheses, and a dy dx. I got it down to 1 dy dx. This is good. This is good news. Now I just need to divide by this whole thing on both sides, right? I'll just ey plus 2y to the minus 3e to the x. That becomes 1, and I write it over here, e to the y plus 2y to the negative 3 e to the x, and there's my answer. So the expression of the slope of the tangent line. This might throw you, but what is the slope of the tangent line? It's the derivative. The derivative is the slope of the tangent line. So they're still doing this game on us where they're using multiple names for the same thing. But I don't know why they want the slope of the tangent line. Well, because that's the derivative. So we're going to put that in there, and then we're going to do the next step. So actually, you saved us some time by those who choose 7. The other class I did the other one, and we had to do this one later. Because they're also going to want the equation of the tangent line, so this is where we're going to go about that. So this is y to the negative 2 e to the x. Let's see, oops, divided by, it gives me the whole fraction, that's good. What do we got? E to the y over plus 2y to the negative third e to the x. But you can see how it really takes focus. Yes, sir.
That was the answer to number 7, not number 8.
Thank you. That's why. Okay, what did I do? Oh, it's up there. We should have done number 8. Well, anyway. I got too excited. Let's see. I can copy and paste. So Control C. Thanks for letting me know. Oh yeah, we're up here. Command V. There we go. Okay. Yes. Focus. I was talking about focus and I'm unfocused. So as you work through these, one rule or one suggestion I have is give yourself plenty of paper. I realized when I was struggling with math, it was because I was trying to conserve paper, and I didn't want to organize my work because I did things sloppy, and I just thought that was good enough. My room was messy. Why shouldn't my paper be? My mom always wanted me to clean my room. My professors always wanted me to make my paper. When I started organizing my paper, it got much better. And it even affected, I started cleaning my room. And I said, oh, I like an organized life. It can get more done that way. So funny how those things happen. But if you give yourself room, work through things slowly, methodically, until you get it down. And then, if you can, some of you will be able to pick up speed. You'll be able to just kind of see things and write them down. But do take the steps in between. Okay? Okay. What I wanted, before we go forward, we're doing okay on time. We've got enough for maybe 2 or 3 more. Notice our answer, our derivative, has both x's and y's. So if we want to actually get what is the slope at a point, we need a point. We need both the x and the y. Up to this point, we just needed an x value. We could plug that in and we'd get our slope. Now we need both an x and a y. And so that's where we're going to talk about maybe like the next one or one of the others where it's the derivative's a little easier to get to, but then they're going to ask us to get the slope at a particular point. They're going to have to give us an x and a y, or we're going to have to find a way to get the x and the y. Okay, so that's what this next part. Any questions on these, on this? Okay. So you got that one. That would be an okay one. This, let's do this. Let's do 8. I think I did 9 on the other class. So if you want to see 9, you can. That recording's there. You could kind of go forward to it. Let me do something a little different. This will be a little easier derivative to take, but the concept that we're doing, because notice they both have 2 parts. They want the expression for the slope of the tangent line, which is what we just did, but then they also want the equation of the tangent line, And I want to focus on how to do that. And that's pretty much the same regardless of whether the derivative was easy to get to or not. Okay? So let's give ourselves a... So notice they're giving us both x and y here. That's the point we're going to use. But this first one, when they say the expression, they want it in terms of the variables. They don't want us to plug in the point yet. So what is the expression of the tangent line in terms of x and y? Well, let's take the derivative, right? 8x squared plus 2y squared equals 16. I'll kind of back up a little bit. This should be a little bit easier. Derivative of the first part, of the first term, 2 times 8, 16. Subtract 1 from the exponent, x to the first power. Derivative of the second term, 2 times 2 is 4. Subtract 1 from the exponent, it's y to the first power. But we took the derivative of y, so we get a dy dx. We get to the equal sign, derivative of 16, that's a constant, it is 0. So notice in this one, no product rule. And we don't end up with 2 dy dx's, so we don't need a factor. We just need to get things that to the other side. So again, I'll highlight, we want to get this by itself. So it's really just, okay, let's subtract 16x. So this becomes, that's 0 for y, dy dx equals negative 16x. And then we just want to divide by 4y because we're trying to get dy dx by itself. That's 1. 16 divided by 4 is negative 4 x over y. Okay, so that's what goes here, not that other thing. Thank you. Okay. Now for the second part, for the b part, they actually want us to get the slope of the tangent line. Remember, the tangent line touches the function at that point that they gave us, 1, negative 2, but it is not part of the function itself. It is a line. All lines have an equation of what? Every line, y equals mx plus b. We need to find a slope. Oh, that's the slope of the tangent line. I can get it from here. And then we need to find the y-intercept of the tangent line. Okay, so we'll do this in steps. The slope, we're going to take this. Let's see, where should I go? Let me go over here. Slope of the tangent line is going to be negative 4 times the coordinate of x over the coordinate of y. Okay, they give us the point up here. X is 1, y is negative 2. Okay, they give us that. And so I'm going to get negative 4 over negative 2, which means that the slope is 2, right? 4 divided by 2, negative 4 divided by negative 2. We so far so good? Okay. So I know my equation of the, I know part of it, it's going to be y equals 2x plus b. I now need to get what that b is. And what I do for that, again, you could also use the point slope formula. It's just like an extra formula to remember. I found a different way to do it. What I do is I just need to find what b is. If I had an x and a y, that would be great, and I do have an x. When x is 1, y is negative 2. So I'm going to plug these into the budding equation that I have going. So y is negative 2. I've got the slope of 2 times x, maybe I should do this, plus b. And x is 1. Okay? So that gives me negative 2 equals 2 plus b. Subtract 2 from both sides. I get negative 4 is equal to b. And so my equation is y equals 2x minus 4. That's the equation of the tangent line at that point. So what you should visualize is at the point 1, negative 2, the function's doing something. You're going to see a tangent line there that has a slope of 2, positive 2, and it would have a y-intercept of negative 4. Okay. And again, you could, well, I didn't try this yesterday. Maybe we could try graphing these with Desmos and see what we get. I haven't ever tried that, but here we put in 2x, bless you, minus 4. Okay? So there's a couple questions that do that. So you're going to need to take the derivative and get that formula, that function, that expression for the slope of the tangent line for the derivative. You're going to plug in the points, both the x and the y, to get that value, to get the slope as a number, and then y equals that number times x plus b. Plug in the points again to find the y-intercept. So that's all algebra at that point. Okay. Let me just, I'm a little curious. 8x squared plus 2x. Let's see. Eight x squared plus plus 2y squared equals 16. Okay. Oh, that's what it looks like. Okay, so an ellipse. I was thinking it should be something like that. And then let's put in our tangent line is y equals 2x minus 4. Whoa, it works. It works. And look at this point is 1, negative 2. Wow. I'm glad I tried that. 20 years of teaching, I never even tried that. But you could, some of these you could actually go ahead and you could verify that before you put it all in. But not only did it verify, I don't know, it's kind of exciting to me to actually see it, right? Instead of this, what are we getting? That's what it is. So, if you're, so you could do this for, like a racetrack. It's an elliptical racetrack, right? This is where the car's going, and this is its slope. If it hit an oil slick right here, where would it go? It would follow that tangent line. That's sort of what would happen. Unless there's kind of a wall to keep them going, something. Okay. So we do have some tools we can use. Let's, I think what we'll do, and again, here's another one. Take its derivative. We get the expression here. Find the slope of the tangent line. So there will still be ones for you to practice on. And notice this will be a little bit more difficult simply because there is a product rule there. And there's two different terms with y's in it. So you're going to have to do the factoring part. But I want to come down here. Here's another one. You get the expression. And then you find the slope of the tangent line just like we did. So the process is going to be the same. And notice we've got one here. I did a slightly different one, I believe, for the other class. So if you want to go into that video and sort of fast forward and find where it is, you could see that example. This is the one I'm going to talk about, both of these. Because notice this, it's sort of the same thing. We've got a function here. We're wanting to find a derivative, and we're wanting to find the derivative when x equals 3. But you can see here there's xy and there's a y there. We're going to potentially, and the derivative will still have a y in it, won't it? It will. But they don't give us a y. They only give us an x. So how do we find out what y is? We put it away till the next lecture. We forget about it. No, we don't do that. What we're going to need to do is to figure out the y's. We go back to the original equation, the one they gave us. We plug in the 3 for x, so that's 3y minus 6,000 equals y. We can solve it for y. So it would be nice if they would have just given it to us and said that this is the point x3 comma something, but they didn't do that. So now we're going to have to solve ourselves. I'm going to subtract y from both sides. So that gives us 2y minus 6,000 equals 0. I'm going to add 6,000 to both sides at the same time. Hopefully that doesn't throw anyone off, but we're doing two things at once. So I move the y to the left and I move the 6,000 to the right. And then we divide both sides by 2. So we get that y equals 3,000. So we were able to find that they're talking about the point x equals 3, y equals 3,000. Okay, we're going to need that once we get the derivative, because our derivative will have both an x and a y in there. So to find the numerical value of the slope of the derivative, we need that. And again, it's not obvious. Those are the ones, and I wasn't joking about it. Those are the ones I would skip and say, okay, I'll have to go to office hours to find out about that one. But then he showed me, oh, that seems so simple. Why didn't I think of it? Because I didn't want to think, right? Part of what we do in the math, your education, we don't know that you'll ever need to do this particular type of question. We're not saying that. Some of you, it might be of help. But what think of this as an athlete, right? Whatever sport you're playing, most sports, they'll go into something like a gym, lift some weights and stuff. Not because their sport lifts weights, not because their sport runs miles. You do that to get your body ready for whatever else you're going to do. This is like that gym. We have a bunch of problems where we help you learn how to think through problems, reason through things, concentrate, and do some difficult things, so that hopefully you'll make some sort of connections that when you're doing whatever you do in your career or your life, that you'll see some sort of connection and you'll be able to solve it. Not necessarily this, but there's this idea of factoring. Sometimes we need to do those things. But that's the goal of education, really, is not to prepare you not to train you for a job, because remember, jobs are always changing. By the time you get out there, we don't know what you're going to have. And not only do we not know what you're going to have in 2 or 3 years, we certainly don't know what jobs are going to look like in 10 or 20 years. But if you know how to learn and you know how to think, that's what all this is about. Okay? So don't get put off too much of thinking, when am I ever going to use this particular thing? Maybe never as a direct thing, but the process that you're learning of thinking through this, that you will use. Okay? And I think and that's it. So notice these last two, that's the only thing that gets sort of added to it. They're going to want you to take a derivative, get a value, but you need the y, and you need to know to go back to the original function, get the y value, and then you'll be good. Okay? So we got a good start. Keep moving through it, and have a wonderful weekend.